Hello and welcome to ThePrint. I am Akanksha Mishra. A couple of days ago, the European Council for Nuclear Research, or CERN as it's commonly known, came out with a groundbreaking paper with research on gravity and antimatter. They tested and proved that antimatter particles fall to the ground in the same way that matter particles do, thus showing that Newton's famous apple test also works on an apple made out of antimatter. The paper is a product of the Alpha collaboration at CERN. And today we have with us the founder of Alpha, Dr. Jeffrey Hangst. Dr. Hangst is an experimental physicist in Aarhus University, Denmark, and he has worked on the paper also. So today he's here with us to share about the research, to tell us more about what it means for antimatter research in the future, and to essentially talk to us about what antimatter is and what its significance is in the scientific world. So welcome, Dr. Hangst. Thank you so much for being here with us today.
Thank you for the invitation.
Let's get right into it. And for our audiences, I'd really love it if you could start by explaining what is antimatter, and can you break it down for us for a layman? And while talking about it, can you also tell us about the history of the antimatter factory at CERN, as you're one of the most renowned places working with antimatter in the world currently?
Okay, so let's start with antimatter. And we need to acknowledge that you and I and the things we deal with in the normal daily life are made of matter, particles and atoms that make up the molecules in our body. That's normal matter. Now, there's an alternative, which we've known about since the 1920s, that for every particle type that we know about of matter, there's a kind of equal but opposite one that we call antimatter. And the main difference is that for a matter particle that has an electric charge, the antimatter particle would have the negative charge, same mass, as far as we know. The other interesting thing about them is that they can't coexist. If they meet each other, they annihilate in really the most violent process that we know about microscopically. So that's where the science fiction aspects of antimatter come in as a fuel for a starship or a doomsday weapon. There's real scientific fact for that. It is a really violent reaction if matter and antimatter meet. Now, the other big puzzle about antimatter is that we believe at the beginning of the universe, after the Big Bang, there should have been equal amounts of matter and antimatter. But the universe seems to only have matter left. And we actually have no idea why, what happened to the antimatter. So this is really one of the big open questions in modern physics. Why is the universe made of matter when there's this other stuff that seemingly would make a universe also if we only use that? So this is really one of the most interesting questions. And it's what really inspires our research here at CERN in this very special facility that we call the Antimatter Factory. So at CERN, we have the only place in the world where we can create particles of antimatter called anti-protons, and then essentially stop them and study them, hold on to them and study them. And that's what I've been doing. I've been working full-time at CERN since 2001, when the latest facility opened. The history of antimatter at CERN goes much further back to the 1980s, when they learned how to deal with antiprotons. But our research is very particular. The laws of physics as we understand them say that matter and antimatter should behave in the same way. And my job is to test that in any way possible. So that's what we're doing now.
Okay, that I think really helps. That really does break it down. Moving on, so about the recent paper that CERN published, that the Alpha collaboration published, tell us more about the significance of uncovering the relationship between gravity and antimatter. What was the theoretical consensus before this, and what do we see now?
Okay, so obviously gravity is very important in the evolution of the universe and its behavior, large scale structure, galaxies and so on. It's gravity that dominates that part of physics. So the modern theory of gravity is called general relativity due to Einstein, and it is very successful. On the other hand, we have a big bunch of unanswered questions. You've probably heard of dark matter and dark energy. Those are things that we have to put into the universe by hand to explain the observations that we have, and we have no idea what they are. So we're really interested in studying gravity, and in particular, since antimatter at the beginning of the universe seems to have disappeared, we wonder, okay, could there be some difference in the way that antimatter falls if you drop it? Okay, so we set out to do that experiment, to actually get some antimatter and drop it, just like Galileo did with his Tower of Pisa experiment so long ago, and see if it actually falls like regular matter. So that's easy to describe. It's very, very difficult in practice to do that. And it's taken more than 30 years of learning how to work with antimatter to actually do this experiment. So that's the significance. This is the first time we've been able to drop some antimatter in the gravitational field of the Earth to see what the result is.
Yeah, I mean, it does make sense why it would be a significant event. And moving on, you did mention that CERN is one of the only places in the world that creates antimatter in your antimatter factory. And I wanted to ask a couple of questions about that. Can you walk us through that? What was the process of creation like? I read that there was a magnetic field that was created, that was manipulated, a trap, as you call it, to put in the anti-protons. And what was that experiment like? Can you walk us through that? And also a second question to that is, since CERN makes its own antimatter, but what about in nature? Where can we find antimatter in nature? Can we?
Okay. So as I described before, matter and antimatter don't like each other. So you really won't find antimatter hanging around. You have to produce it. And here it also, again, goes to Einstein with the most famous equation in physics, E equals mc squared. What we do in CERN is use energy E to make matter with mass m, right? That's our business. We're always trying to discover new things by creating them using high energy collisions. So at CERN, we make anti-protons, which is the nucleus of the anti-hydrogen atom. Okay, so hydrogen is atom number one, the most ubiquitous substance in the universe, the fuel for stars, number one on the periodic chart, just one proton, one electron. We make anti-hydrogen at CERN. We're here because they give us the antiprotons. It's the only place in the world that will provide us with antiprotons to make our anti-hydrogen atoms. So CERN sends them to us at fairly high velocity, and then we stop them and trap them in electromagnetic fields. Okay, antiprotons are electrically charged. They have a negative charge. So we're pretty good at manipulating charged particles using electric and magnetic fields. Of course, all this happens in a very high vacuum. You can't have any matter around, so you have to pump out all the matter.
Yeah.
So this is all extremely technically challenging, and it's taken, as I said, about 30 years to develop. Now, with gravity, you need something that's electrically neutral. You can't have a charge because gravity is by far the weakest of the four forces that we know about. That may go counter to your intuition because, if you fall down, it's gravity that's going to knock you over, but it's actually electromagnetism that breaks your leg, not gravity. So on the scale for physics, gravity is very weak. And so if you had a charge, it's very difficult to observe it compared to other forces like electromagnetism. So we've been working for a long time to make neutral antimatter. And ALPHA is the only experiment in the world that knows how to make neutral antimatter and then hold on to it. Now, when it's neutral, you hold on to it because it's a little bit magnetic, but it's very, very difficult. And we've only been doing this for the past decade. And now what we've done is make an experiment where we put some neutral antimatter in a magnetic trap, a bottle, and we release it to see what happens. So that's the essence of what we're talking about today.
Okay. Thank you for that. I think that's really helpful. Moving on, I mean, since our viewers would also want to know more about antimatter itself, can you tell us some of the scientific uses of antimatter, where it's used around the world?
Okay, so again, antimatter doesn't occur naturally except in rather rare isotopes that emit a positron, an anti-electron. The most common use of antimatter in daily life is in the hospital, in something called a PET scan, where they'll actually inject you with a substance that's emitting positrons, which are anti-electrons. So PET scanning stands for positron emission tomography. They're actually injecting you with something that emits antimatter, and then when that antimatter annihilates in your body, it creates a signal that they can use to do a medical image. So, of course, you have to produce this substance, and it decays rather rapidly, but that's an everyday use of antimatter. You can actually get injected with a substance that emits antimatter. For the most part, antimatter... Go ahead.
That's really interesting. Yeah, please.
Yes. Yeah. So for scientists like me, we're interested in the fundamental open questions of the universe. And antimatter is this extremely mysterious stuff. So, I mean, we're kind of obligated to study it as well as we can. It's so cool to be privileged to be the first people to look at something like this and kind of reveal any mysteries that may be there. So the question is there something slightly different about antimatter that we don't know yet? The theory predicts symmetry, but maybe it's a little bit different and we just haven't looked carefully enough.
And I think scientists at CERN are doing a very good job of unraveling this mystery for us. So moving on, can you tell us, as part of CERN and as part of Alpha, what has this experiment resulted in you knowing more, and in the world knowing more about antimatter? And what are the future prospects of what this research has enabled you to do in studying the properties of antimatter and telling us more about it?
Okay, so for the current experiment, we dropped our antimatter and we detected what happened to it. And we were able to determine that, okay, within the uncertainty of the experiment, it behaves just like normal matter. So, if you drop something in the field of the Earth, there's an acceleration that we've measured, 9.8 meters per second squared. Everybody knows the number from high school physics. Antimatter does the same thing, as far as we can tell. Now, the general theory of relativity predicted that, but no one had ever been able to observe it before. So this is a huge step in our understanding of antimatter, that we're not just working with theory now, we're actually measuring what happens to it. So for us, for us, it's really a huge moment in antimatter science to be able to verify that. Unfortunately, it doesn't give us any clues about what might have happened in the Big Bang. If they behave equally, then there's still a big mystery. But we're not done yet, because this experiment, while it's groundbreaking, it can be more precise. We can do a better job of this in the future. So you ask what comes next. That's what comes next. We'll try to make this measurement much more precisely. So now we know that it's going to go down. We'd like to know that it goes down in exactly the same way as normal matter, as far as we can measure. Okay, so that's the current experiment. The other thing that Alpha does, and has been doing for quite some time, is to look inside the atom of antihydrogen to see if it has the same structure as hydrogen. Hydrogen is the atom we know best. We learned how to do physics by studying hydrogen. Since the early 1900s, we've been looking carefully at hydrogen. So it's just obvious that if you can make antihydrogen, you need to compare it very carefully with normal hydrogen. And we actually have two separate machines in Alpha, one that does the internal structure measurements and one that does gravity. So we have, 10, 20 years of work ahead of us to really narrow down the properties and make sure that there isn't some small difference.
And can you tell us a little bit about the upcoming Aegis experiment, which is supposed to measure the gravitational force on a beam of antimatter? Is that, what can you tell us about that?
Well, that's a completely different approach than ours. And they actually started a long time before we did. So they've been making progress, but I can't tell you where they stand today. The only thing I see from them is we have a review every year
Okay.
of all the experiments here at the Antimatter factory. And so they make a presentation once a year where they talk about their progress. I don't think they're going to have any result anytime soon. There's a third experiment called G-bar, which is also making progress in the same direction, again, with a third approach. But my impression is they're not that close yet.
Okay. Just a few general questions about the team that worked on this current project.
Yes.
Can you tell us more about the team, what it consisted of, and what, I mean, you said that you have been working on this for over 20, 30 years. I'm sure a lot of experience and a lot of steps went into this. But what can you tell us about the team that worked on this paper that was released, and where are they from, and just...
Okay, yeah. So Alpha started in 2005.
Okay.
And we're right now about 60 some scientists from all over the world. That sounds like a lot, but that's really small for a CERN experiment, which can easily have 2,000 physicists on the big experiments at the Large Hadron Collider, the LHC. So I think we have 16 or 17 institutes now from all over the world, from Israel, Brazil, United States, Canada, the UK, Denmark. And it's an interdisciplinary collaboration. We have lots of different types of experts.
Okay.
Because to make this antihydrogen and study it, there are many different disciplines of physics that are necessary. It's a really fantastic team. I'm really proud of them. But yeah, we've been around. We're going to stay around. We have a lot of good work coming up. It's a real pleasure to be able to work with these people.
That's great. Thank you so much for being with us today, Mr. Hangst. And all the best on the future endeavors of CERN's Alpha. And thank you. Have a good day.
Thank you very much for your interest in our work and a lot of great questions.
Thank you.